So we'll just review from last week a little bit. And when we make a buffer, what's the first thing we look for? Well, what is our desired pH? Our desired pH for that example was a pH 7 because we wanted to compare that to just water. And so if I wanted to make a pH 7 buffer, what's the first thing you do? What's the first thing we did? So this is probably something that's good. I mean, what you do is you go back through on Thursday's notes, and then you make little key points. And one of the key points is in the first step, what did we try to do in making a pH 7.00 buffer? Yeah, why did we want an acid with a pKa 7? So this is, you make a little annotation. Why do we want that? So what we do is we look for pKa, ideally around 7, but the pKa, -1 would be the minimum to a pKa +1 would be the maximum. And what did we call this? Do you recall what we called this? Yeah, or not the buffer region, we called it the buffer range. And do you recall why this is the buffer range? I had mentioned it, but maybe you didn't catch it. It's called the buffer range because if we want to keep the base to acid ratio as close to what as possible? As close to, the ratio. How many parts of base, do you want it 50-50, or do you want 75-25, or do you want it 1 million to 1? What do you want the base to acid ratio to be ideally? I had something called the ideal pH, or maybe I should review a little bit further back. Because for buffers, pKa, if we had a buffer, this is why we spent so much time. How much time did we look for an appropriate acid for a pH 7.00 buffer? I think like 15 minutes or 20 minutes we were looking. And the purpose was to do what? To get something with a pKa 7. And we had 2 or 3 acids that had a pKa right on 7. Why didn't we use those? Yeah, other difficulties, but those would have been great if they would have worked, because we would have had a 1-to-1 ratio. And so if we're at a pH and a pKa of 1-to-1, this is 1-to-1. 1 part of base to 1 part of acid. And that makes the most versatile buffer, because a buffer should be able to handle added acids and added bases with equal ease. It shouldn't be what I said, lopsided. Lopsided is my word. Because if we're at a pKa -1, what does that mean the base to acid ratio is? This is base to acid. If we're at a pKa -1, that means the base to acid ratio is?
Favorable to acid and more acid.
More acid. Yeah, how much more acid? 1 to 10, yeah. It's a 1 to 10 ratio. All right, so this is lopsided because we have way more acid, 10 times the amount of acid than base. Well, if you make it concentrated enough, it's okay, but do you want to go even more lopsided? Not really. I mean, you could, but it'd be too lopsided. And likewise, at the top of the range, what is it? 10 to 1. And so we try to keep it in this range to make it not too lopsided. Over here on this side, it's way more base. Over here, it's way more acid. And so it would be, you know, and so this is called the buffer range. It has buffering ability out. You know, we could get in this lopsided range. You know, it just doesn't make a good practical buffer. The Henderson-Hasselbalch equation can be used over a much wider range. So this is another point. The Henderson-Hasselbalch can be used almost from one end to the other. When I was marking up the pH titration curve, I marked it. You know, the plus or minus one's important. The plus or minus one is 1/11th and the 10/11th. So you can see, you know, that's the buffer range for this. The HH equation could be used over a wider range than this. It could be pretty lopsided as long as the SA is valid. And for the SA to be valid, we need reasonable concentrations here. If the buffer becomes too dilute, it's going to go to pH 7 regardless. So we were looking at capacities. What was the ratio that we came up with? Okay. So 0.634 base to 1 part acid. So we came up with this ratio. We could flip it. It just has to be that ratio, so we could increase it. In fact, I'm going to flip it. I'm going to try to keep the numbers simple. So I'm just going to invert 0.634.
There was no 4, it was 0.630.
Oh, 0.630, thanks. So if I invert 0.63, then I get 1.587, which is equal to a 1 to 1.587, which is equal to, etc. So what we can do is we can increase the capacity or decrease the capacity. Here, I showed that with the 0.63, but let's do it with this one here to make it even maybe a bit easier as far as the numbers go. And so let's go with, do you think 10 molar, is it possible to make 10 molar? It might not be possible to make 10 molar because you got to put 10 moles of salt in a liter. Will it all dissolve? And so so if I want 10 molar and 15 molar, let's go 10 and 15.8 or 15.9, 15.87. If I did something like this, molar, the base for ours was HPO4 2 minus, and the acid was H2PO4. And so both of these are amphoteric, but when you have them together, then this one will be the acid, this one will be the base. This might exceed, so the question mark is, does this exceed the solubility? You know, we can't have, maybe, probably can't have that. Something like that. And so we'll pick maybe something a little bit smaller. Maybe let's try to double it. So if we double this, maybe we'll go with 2.00 molar and 3. What is that? 80, 60. Oh, we'll just do it times 2. 3.174. Maybe something like that might be, you know, this would be pretty high capacity. You know, the more concentrated, the higher the capacity. But you might say, okay, let's just try to save money. If we try to save money, maybe we'll just dilute this by 1,000 times, so, or maybe 10,000 times. Maybe we're going to save a lot of money this way. And so if we go 0.00100 molar for the base, and then we'll go 0.00157 molar for the acid. We could save a lot of money, right, with this. And so this would be lower capacity. So this may not be possible. These concentrations are fairly high, you know, and we might not be able to get there.
Capacity also dependent on the strength of the acid base.
No, just the moles of acid that are contained in there. You know, what's going to depend on the strength is how reactive it is. You know. But normally, well, it could. Normally, when we're thinking about capacity, we're adding strong acid or strong base. And so, if your acid is too weak, and then you're adding an even weaker base, then you might not get as much. But the pH isn't going to change much either way if everything's weak. You know. So let's just pick these two as examples. So and what did we decide? We're going to add strong acid. Is that correct? Or strong base? Yeah. Okay. We already added 1 drop of strong acid to water. And water is pH 7. Now we're going to pick this buffer. We're going to use the higher capacity first. So let's look at the impact of 1 drop of 6 molar HCl. I'm going to increase the sig figs here, but essentially on the high capacity buffer first. So the buffer, if we add the acid, we're going to have the strongest acid, which is going to be HCl, reacting with the strongest base present. And in the buffer, the base component is HPO4 2 minus. So strongest acid plus strongest base. And this is going to produce Cl minus plus H2PO4 minus. And the K for this is very, very large. So we expect it to go to completion. But before I do this, I have to do a step. What's the step I have to do before this? Solution dilution. Now, buffer capacity is also going to depend not only on the concentration, but also on the volume. Let's say I had 5 milliliters of buffer versus 5,000 milliliters of buffer. You know, one drop is going to have a much greater impact on 5 milliliters of buffer than 5,000 milliliters of buffer. And so buffer capacity also depends on volume. So we go 5 milliliters of buffer versus 5,000 milliliters or 5 liters of buffer. And the 5 liters of buffer is going to have definitely a larger capacity. And so this is lower capacity, and this is higher capacity. And so two things that will influence it. And so you could have low concentration, but if you have a very large volume, then that compensates for it because it depends on the number of moles in the long run. And so how much water did we start off with? Can you remind me? Was it 25 milliliters of water? Okay, so we're going to go with 25 milliliters of buffer. And so the first step, you know, before I do this, I have to do the solution dilution. So step I. So first I got to pick out how much buffer I want. Well, I'm going to go with 25 milliliters because that's what we use for the water. You know, obviously if I use more, it would be higher, and if I use less, it would be lower capacity. And then I'm going to end up with, actually I need to increase the sig figs in order to make this significant, so I'll just go ahead and do that on the fly here. So this is going to be 25.05 milliliters of reaction mixture. Now the HCl is the same dilution factor. It's going to be a 0.05 to 25.05. And I'm going to add some more sig figs here, so let me kind of ignore them. Of 6 molar. And so what was the concentration of the HCl that we had before? Should be the same. What was it? Oh, I mean after dilution. Oh, I got it here. It comes out to 0.01197. Okay, now we have to calculate the concentration of the buffer components. So the buffer components is, we'll have the acid component, H2PO4 minus. The acid component is going to be, what's the dilution factor? The dilution factor is going to be a 25.00 over 25.05 dilution. And the molarity that we decided to use was this one. The acid is going to be 3.174 molar. And so I'll do a 25 over 25.05 dilution of 3.174. This is going to come out to 3.167 molar. And so it didn't change much, really. The base, I'm going to have to make some room here, so let me do that. The base component was the HPO4 2 minus. And the dilution factor is the same. It's a 25.00 to 25.05 dilution. But the concentration's different. The concentration is not the same because we needed less base to drop the pH by 0.2 units. It was 2.00 molar. And so let's go ahead and do that. There's a 25 divided by 25.05 dilution of 2. 1.996. If I didn't carry these extra sig figs, nothing changed. You know, since I'm carrying these extra sig figs, you know, we started with 3.17 molar, we end up with 3.17 molar. We started off with 2 molar, we end up with 2 molar. If I round it, but I don't want to round this, I'm going to carry extra digits right now. Now, what a buffer is supposed to do is it's supposed to resist pH changes. So, for example, when I added the drop of water, the drop of HCl to the water, the pH changed dramatically. The pH changed by 5 power units. 5 power units would be 10 to the 5th, which would be 100,000 times more acidic. And so if I add this drop, what we don't want to see is we don't want to see a large pH change. So for example, if your blood is what, pH 7.2? If your blood changes from 7.2 to 7.3, is that a big deal? Or what if it goes from 7.2 to 7.5? No big deal? What do you think? It's not a big deal? I think 7.5 is lethal, isn't it? Yeah, I think you'd be dead if your blood pH changed by that much. So maybe what we need to do is we need to get, let me back up a step and let's talk about power functions, because it's hard. You know, unless, like geologists are totally into power functions because of the Richter scale. So for example, if you had an earthquake that was 6 on the Richter scale versus one that's 7, you think, oh, 6 to 7, no big deal. But you know, a 7 earthquake is like 10 times more powerful. 10 times more powerful is hugely significant, I think, in terms of that. You know, and so they're talking about an earthquake with, let's say, of a 9. You know, earthquake of a 9 versus a 6, you know, 1,000 times more powerful. And so, since it's tricky because we have to get used to thinking in terms of both the X, you know, in this case Ka or concentration or something, and the Px. The Px would be the power function of X, or the pKa. So when you look at these, you know, can you translate these to pKa? You know, can you visualize what the pKa should be? And so maybe what we should do is, let's do something really quick in Excel, because we could do this pretty fast in Excel. Let's start off with something like 1 times 10 to the minus 8. If I have 1 times 10 to the minus 8, then let's calculate the power function of that. That would be equal to the negative log of this number here. And what is the power function of 1.00 times 10 to the negative 8? It would be it would be 8, right? How many sig figs would we have in this power function? Right now, how many sig figs are there? 0. So I need to go 2 decimal places. That's way too many. Now I have 2 sig figs. This is telling me it's right on 10 to the minus 8. That is, it's 1 times 10 to the minus 8. Oh, it is 3 sig figs. This is 3 sig figs over here, so I need 1 more. You're right. So let me increase that to 3 sig figs. All right, then I'm going to go, how about this? I'm going to go, let's go down to 10 times 10 to the minus 8. 10 times 10 to the minus 8 is bigger, right? So we'll go with 2. I don't know if Excel can do an uptrend. 3, 4, 5, 6, 7, 8, 9, 10. You know what Excel is going to do to my 10 times 10 to the minus 8? It's going to change it to what? It's not, when I hit the enter key, what's Excel going to do? It's going to change it to, yeah, right. It's going to change it to 1 times 10 to the negative 7, which is bigger. And what's the pH of this? Or P, whatever, P, the power function? It'd be 7, right? Okay, now let me ask you this. What if I had 5 times 10 to the minus 8? So 1, 2, 3, 4, 5. 5 times 10 to the minus 8. So I'm going to go halfway between. So I'm here at 1 times 10 to the minus 8 to 10 times 10 to the minus 8. If I go 5 times 10 to the minus 8, is it going to be a pH of, or pKa or whatever, power function of 7.5? Is it linear? Is this a linear scale? So should it be 7.5? Here it's linear because I'm going halfway between these two, although I need to insert one more column here. Let me try that.
It's not linear.
Is it? No. And so what is it? If I'm halfway between these two, what is the power function going to be? It's not halfway. Is it going to be like 1/3? What would you guess? Smaller than 7.5 or bigger than 7.5?
Bigger.
Bigger than 7.5? Let's take a look. But, you know, 50-50 is worth. And so it came out smaller. And so it's sometimes some people are into this. One of the homework problems, they ask you, if the pH changes by this much, how much did the concentration change? Sometimes they make an empirical equation based on that. You know, and so let's take a look at how the let's take a look at how this changes. And it's kind of weird how it changes. So, so we're making it more concentrated. So we start off with 10 to the minus 8, which is pH, let's say 8. And then we make it more concentrated. As we make it more concentrated, yeah. So the point is the relationship is a little bit more tricky than what you expect. And so that's about it. And so when we look at these numbers and then try to relate that, it's hard because the coefficients change this in a nonlinear fashion. And so when we're looking at a table like this, it's hard because the coefficients are changing it. So if I have 6.3 times 10 to the minus 5, I would think, okay, if I'm at 6.3 times 10 to the minus 5, that's getting close to 10 to the minus, 10 to the times 10 to the minus 5. 10 times 10 to the minus 5 would be 4. So this would be a pKa of 4. So I would think this is getting closer to pKa of 4, but versus 5. You know, it's closer to 4 than 5. And so I go back over here and I go, okay, 6.3 times 10 to the minus 5. What is it? So I was suspecting it's getting closer to 4, and so maybe it worked out okay. All right. So when we this is when we're trying to choose the buffer system, so you have to be careful sometimes with that. But there are clearly buffers that are not in the range. And so this one would require, if I wanted to make a pH 7 buffer from this, it's too far away. This is almost 3 orders of magnitude. 3 orders of magnitude would be, okay, now this is kind of weird too because of the way it would go here. If I tried to use this acid for my buffer, how far off would I be? Well, if we go back here, you know, I need to go not +1, not +2, I need to go +3. So what kind, how lopsided is this buffer? Well, okay, +2 would be 100 to 1, and +3 would be 1,000 to 1. So this would be way too lopsided. I wouldn't want to use this system. So just be careful with the powers of 10 thing. And so this is kind of why we try to get it as close to 7 as possible. Better save this. I would have posted these notes, but Word keeps crashing for some reason. All right, so here the HCl, we have after solution dilution 0.01197. HPO4 2-, we have 1.996. Chloride, we have 0. H2PO4-, we have 3.167. These are all molar. Now, your book uses moles sometimes, but at the end they have to convert it back to molarity. You could use moles or millimoles if you prefer. Limiting reagents, HCl. The excess reagent is the HPO4 2-. So the limiting reagent is going to go to 0. And so we're going to lose that here, 0.01197. So I'm just going to use the calculator. 1.996 minus 0.01197. I should probably get it to the same number of decimal places, but it's all right. So I get 1.998403. Did that correct? I have way too many digits there, but it's all right. Over here I'm going to have plus 0.01197. Over here I'm going to have plus 0.01197. And so 3.167 plus 0.01197 is a 3.17897 molar. Now, chloride's neutral, so we don't really worry about it. What we have left over, though, what do we have left over? We have an HH buffer left over. In fact, we have the same HH buffer. And it changed the ratio a little bit. Did it change the ratio by much? Let's take a look. If it's an HH buffer, we're going to have the pH is equal to pKa. The pKa we calculated earlier was 7.20 plus the log. We'll take the log of the base, which is HPO4 2-, so this is going to be 1.998403 over the acid. Now the acid is 3.17897.
Wait, how do you see that was an HH buffer?
Because it's the base and acid conjugate pair. In fact, it's the same base and same acid as we started with. So I'm going to take the log of that and then plus 7.2. And I get a pH of 6.99839. And then round it. When I round it, it rounds to 7.00. Did the pH change significantly? No, the pH didn't really change. I started with a pH 7 buffer here, pH 7.00, because I put them in the right ratio to make it 7.00. By lowering the pH by having about twice as much acid, or less than twice as much, 1.58 times as much. And so there's insignificant change in the pH. And so that's a good buffer, right? A good buffer should resist it. All right, what if we did the same thing to the low capacity buffer? How would that impact low capacity? Now we could do low capacity in two ways. We can decrease the volume, or we could decrease the concentration. We're going to keep the volume the same, 25 milliliters. What we're going to do is decrease the concentration. So we're going to start off with 25.00 milliliters. And then we're going to add 1 drop. And so let's calculate the solution dilutions here. HCl is going to be a 0.05, 1 drop. And I'm going to carry extra sig figs just so you don't have to worry about it. And it's still 6 molar, so it's still going to be 0.01197 molar. Then we'll go to the acid component here, H2PO4 minus, which is going to be a 25 to 25.05 dilution of, what was the concentration of the low 0000100 molar. It's barely diluted. But nonetheless, I'm going to calculate it. Quadruple 0, 998 0 molar. So it went from 100 to 998. So not much dilution. And then the HPO4 2 minus, this is also very mild dilution. It's 25 to 2505 dilution. And the concentration of this is 1587. I'm carrying extra digits, so these dilutions are very small, but I want to see it. I don't want to round things, otherwise it looks like nothing's changed. And so 25 divided by 25.05 times 0.000 1587 is going to give me 1588. So 000 15. How could it go up? 83, sorry, 1583. 838. So it went down. It went from 1587 to 1584, roughly 1583.8. And so, still pH 7. You can dilute buffers. It's not going to change the ratio. And so we could dilute this even more. Ratio is going to stay the same. The pH should stay the same until you overly dilute it. When you overly dilute it, then it's going to go to pH 7, but this is a special case because our buffer was already pH 7. If your buffer was pH 4, then you don't want it to go to pH 7 by over dilution. Did you hear about these pharmacists that dilute the medication? You heard of that? There have been a number of criminal cases where the pharmacist, there's people who need this, like chemotherapy agent or these critical drugs, and the pharmacist is diluting it so they can make more money off of it. It's just pretty unbelievable. But you could do the same thing with buffer. If you're selling buffers, maybe you could just dilute it down. You could sell it pH 7 buffer. But is it going to be very effective? Well, let's see if this buffer is going to be very effective. So let's take our HCl. And then the strongest base present is going to be HPO4 2 minus. And we get the same reaction. We're going to get chloride and H2PO4 minus. The HCl is 0.01197, 1197 molar. The HPO4 2 minus is 0.000158338. The chloride 0. The H2PO4 minus is quadruple 0, 9980 molar. So when you look at the limiting reagent, what is the limiting reagent now? This is the limiting reagent. And so what we say here is we've exceeded the capacity. If we completely eliminate one of the components, then it's no longer going to be a buffer. And in fact, what we're going to end up with is a more significant pH change here. So if I set up my ice table, again, the limiting reagent goes to 0 molar, and we're going to lose 0.00015838. Which is going to give me 0.011811162. And this is, the chloride is not going to have any impact on the pH, so we're not going to worry about that. And then we have this, the weak acid here. Here we're going to add point 1,000,015,838. So I'm going to calculate it. Point quadruple 0, 99, or just 998, plus point 1,000,015,838 gives me 0.000,25818 molar. So what we have here is we have a strong acid plus an amphoteric. And so essentially this is like a strong acid, weak acid solution. In a strong acid, weak acid solution, the pH is going to largely be dictated by the strong acid alone. And so I'm going to just ignore the hydronium ion contribution from the amphoteric species and just assume that, and it's a decent assumption, that the pH is going to be from this. And so we'll take the log of 0.011811162, and I get a pH of 1.927, pH of 1.93. So, so the buffering capacity is related to how many moles of acid or how many moles of added base you can neutralize. So the more moles, the higher the capacity. It's also going to resist change more significantly. The higher the concentration you have, the smaller the impact one drop will have on it. So let's say if you had a lot of gold coins, then if you're missing one, it's not so significant than if you just had one, two. All right, so this was a little extreme. We exceeded the capacity. We don't want to exceed the capacity of the buffer, so we have to make sure when we make a buffer, we make it with enough capacity for its intended use. So sometimes we reuse the buffer, but you can only do that to a certain limit before the buffer is no longer any good. All right, are there any questions on the buffers? We have a wide range of acids here. And so we could make a wide range of buffers. We could make buffers all the way from pH 1. Actually, we can probably go from pH 0 all the way up to pH. Let's see, let's take a look. (13), 14, probably all the way up to pH 14, from 0 to 14. We pretty much have it covered. It's not that they're going to be good buffers. Some of these are quite toxic.
Can you make buffers above or below 0 and 14? Using superacids for this?
The problem is okay, when you get to a certain point, the conjugate base or the conjugate acid doesn't do anything. So let's say if we try to make a buffer, this is very common, using, okay, I want to make a very low, like some negative pH buffer. And so I might pick like a strong acid, like HCl, and mix it with chloride, its conjugate base. And so here's my acid, here's my base, and this could bring the pH way down because HCl is a really good acid. But will this make a good buffer? And this won't make a good buffer because chloride won't neutralize anything. Even though it is the conjugate base, it's a worthless base. And so we can't use this. It has to be both have to be weak, because that way the conjugates are still okay. They're moderate. But if you have a strong, whether it's a strong acid like this, its conjugate base is going to be worthless, or if you have a strong base, its conjugate acid is going to be worthless. So you'll have one half of the buffer great, but the other half totally worthless. And so this is why we can't use a strong species in a buffering capacity. Are we okay with that? All right, now the next thing I'm going to talk about are indicators. A typical indicator is like a weak acid. And its conjugate, is a weak base. They're kind of moderate things. And these have to be conjugates of one another. But the key for this is that the weak acid has to have an acid color. And the acid color has to be different than the base color. So this is what's going to happen. If I add a drop of indicator and I neutralize it, so let's say I add a drop of phenolphthalein. Phenolphthalein, the acid color is colorless. They make a buffer system. They don't have to be a buffer to start with, but when you start, let's say we start off with just pure acid. If we start off with a pure acid, it's not a buffer. But when we start adding our titrant, the sodium hydroxide, not only is it neutralizing our acid that we put in there, it's also neutralizing the indicator. And so this is why I say don't use too much indicator. You know, some people want to put in a lot of drops of indicator because then we'll get a more intense color. But the more drops of indicator you add, the more acid you have to add, base you have to add to neutralize that. And so whatever you do, you always add the same amount of indicator for each run of titration. And I usually recommend just 1 drop, because 1 drop is usually enough to see it. Okay, right there. Red. This should be just red. So the acid color is colorless, and the base color is red. But what's going to happen is we're going to transition. We're going to make like a titration curve for the indicator as well. And so if we make it like a titration curve for the indicator, then what we're going to see is this, basically. If both are present, this is a buffer system. And we're going to have both present during the course of the titration. Initially, it might not be. And maybe at the end, it might not be. At the end, we would have neutralized all our indicator. But in the middle, for sure, it's going to be. And so what we have is we have this. The pH is equal to the pKa of the indicator. Plus the log of the base to acid ratio for the indicator. The way it turns out for indicators is like this. If we have a pH that's equal to the pKa, then what's the ratio of base to acid? Okay, first, what is the pKa of phenolphthalein? The pKa of phenolphthalein is around 8. So if we have a pH around 8, and that's equal to the pKa, what's the base to acid ratio? 1 to 1. So we have a 1 to 1. You know, what does a 1 to 1 mixture of red and colorless look like? Pink. If we have a pKa plus 1, let's say we're looking at a pH of about 9. What color is it going to look? Red. Because we're going to have a 10 to 1 ratio, 10 parts of base to 1 part of acid. And so the base color dominates. So we could go to pKa plus 2. It's still going to be red. pKa plus 3. It's still going to be red. Because here we're going to have a 100 to 1 ratio. Here we're going to have a 1,000 to 1 ratio of red to colorless. And so red will dominate here. If we go to pKa minus 1, then the acid is going to dominate because it's going to be 1 to 10 ratio. And so here, if we have a 1 to 10 ratio, it's probably going to be colorless. You might see a faint color, but probably not. A pKa minus 2, it's definitely going to be colorless because it's going to be 1 to 100 ratio. 100 parts of colorless to 1 part red. This is going to be colorless. On a pKa -2 is going to be 1 to 1,000 ratio. And so 1,000 parts colorless, 1 part red. And so this will be colorless as well. So when we look at the indicators are like buffer systems, but now we look at the base to acid ratio to tell us the color. If the base to acid ratio is greater than 10, the base color dominates. If the base to acid ratio is less than 1/10, then the acid color dominates. But if the base to acid ratio is between 1/10 and 10 to 1, then we have an intermediate color. And so what we can do is we're going to take a look here at indicators. Let me see. Yeah. It's all weak acid, right? And so I'm going to go to the titration curve, which page was that, 720? $780, I guess it was. Well, maybe we'll take a look for indicators first. So this is what they're showing here. This is buffer, sorry, indicators. And so they have to have different colors. The acid color, IN stands for indicator, so it's whatever the anion for the indicator is. And IN minus, that's the indicator negative, the anion. And here they do the pKa of the indicator, plus the base to acid ratio. And so, for example, bromethymol blue has a pKa of 7.1. So that means at 6.1 and below, it's yellow. And the 8.1 and above, it's blue, because the acid color is yellow and the base color is blue. But in between 6.1 and 8.1, we have a mix. And so when you mix yellow and blue, do you know what color you get? Green, yeah. And so this is what we were just talking about, the ratios here. So we have all different kinds of, we have extremely weak acids like alizarin. Alizarin yellow, the acid color is yellow. So it goes yellow all the way from below 0 to about 10. And above 12, it's base color. It's violet. And between 10 and 12, its pKa is around 11. It is intermediate. And so violet and yellow makes this color, whatever this is. This one would be tough because this goes from, well, no, this would be easy because it goes colorless to colored. And so you'd be looking for that. And the pKa would be around 10. Here's phenolphthalein. pKa is around 9. Oh, did I say around 8? Shoot. I probably have to correct that. pKa is around 9. And so the intermediate color is around here. Let me correct that. I don't know exactly what the pKa is. So around 10. And then over here, pH around 8. pH around 8 should be colorless. pH around 10 should be red. In between 8 and 10, it should be pink. So let's take a look at that again. Around 10, it's colored, roughly, a little bit below. Solid red all the way. And so this is 10 to 1, 100 to 1, 1,000 to 1, etc. Vice versa. And so we have all these indicators. And you can see there's a whole bunch of acids which have different colors than their conjugate base. And they span wide range of pKa's, so we have a lot of indicators that we can select from. The indicator can only tell you, the intermediate. So if you're yellow, it doesn't tell you anything, because yellow just means the pH is below 10. If this is violet, then it tells you the pH is greater than 12. You want that intermediate color to pinpoint the pH. The pH meters are good for this. And then we can select the indicator depending on where we expect the equivalence point to be. And so in a strong acid, strong base titration, we expect the equivalence point to be pH 7. But here they're using phenolphthalein. Phenolphthalein doesn't change until around 9. That's when we see the light pink color. So if we're at pH 9, we've overshot, because we've neutralized the acid at pH 7. But is that going to lead to an error? Yes, it's going to lead to an error. Is it going to lead to a significant error? And so we'd have to determine it. 1 drop is 0.05 milliliters. So if we go 0.05 milliliters, do we even get 1 drop error? No, it turns out it's less than a drop error. And it's a systematic error because you do all your titrations, including the standardizations, with phenolphthalein. So you're always going to be off a little bit, and that error cancels out systematically. So phenolphthalein is the indicator of choice here. Although bromethymol blue would be perfect, because bromethymol blue turns green here, and there wouldn't be any error. But since the error is so small, because this curve is so vertical, a huge change in pH resulted in a tiny change in volume. That's fine. Whereas over here, if we use something like thymol blue has an enormous range in volume for this. The volume would be here all the way up to here. So thymol blue would not work. That's for a strong. Now if we go to a weak acid, strong base, then phenolphthaleine's perfect. Where was that? I think it was 4 pages up. Whereas bromethymol blue might work. It changes at 7. It's still kind of in the vertical part here. But if you caught it down here, you're looking at a much bigger error if you caught it early. If we use bromethymol blue here. And so bromethymol blue probably wouldn't work because this vertical range is too short. But phenolphthalein works quite nicely. So phenolphthaleine's the indicator of choice for titrations. It's easy to see. All right, so in chapter 17, we're looking at different kinds of mixtures. There's one last titration, actually a couple of more. We have, instead of putting the sodium hydroxide in the burette and titrating the acid, you could put the acid in the burette and titrate the base. If you titrate the base instead of the acid, what's the curve going to look like? It's just, it's going to be just flipped. Probably won't do that. This is it. This would be flipped. Strong base being titrated. And the same thing, if you had the strong base being titrated with a weak acid, it'd just be flipped. The other type of titration is weak acid, weak base titration. If we have a weak acid, weak base titration, This is kind of like a buffer solution, right? But this is a buffer solution we have to solve by a simultaneous method. We can't use the HH because usually the weak acid and the weak base are not conjugates of one another. If they're conjugates, then it's just an HH buffer. And so if you're trying to titrate two conjugates, you expect no reaction. You're just making a buffer. But here, let's say the acid and the base weren't related, then this is just a buffer in which we have to use the simultaneous. And we don't expect the pH to change much. The pH shouldn't change much. Of course, the ratio, it's going to go up or down. If you're adding base to it, it's going to go up. pH shouldn't change much. And so we don't get a distinctive structure in the titration curve, and therefore we're going to ignore this, plus it's simultaneous. So this is another reason to ignore it being simultaneous. Now, do we really have to ignore it? Well, we're going to ignore it for Chem 1B, but do we really have to ignore it? No, we don't, because we could try to attempt to solve it simultaneously. So let's give an example here of one. Pick a weak acid. All right. Hydrofluoric, and pick a weak base. Acetate. All right, we'll do sodium acetate. Hydrofluoric acid and sodium acetate. How am I going to figure out what the pH of this is? Okay, one, does this react to completion? Is K very large? No. We're going to make acetic acid and sodium fluoride. K is not large. We could try to figure out what K is by combining equations. But we know it's not large. Not very large, I should say. So for example, if we combine the Ka of HF plus the Kb equation for sodium or for acetate, then that could work. So it would be Ka for HF times Kb for sodium acetate. That would give it, because the hydronium and hydroxide, we need Kw also. So we can figure out what the K is for this by combining equations. But once we get the equilibrium concentrations, then what do? We have a mixture of a bunch of acids, well, not a bunch, but two acids and two bases. Then what do? Should I do a Ka, or should I do a Kb, or what should I do? Where's my hydronium, where's my hydroxide? And so basically what you're going to do is you're going to sit there and you're going to figure out that you're going to have to do a Ka plus a Kb plus a Kw simultaneous. Now the simultaneous that I did was only 2 equilibria. What happens if you have a simultaneous with 3 equilibria? Is it equally as bad or worse? What do you think? Worse. It's going to be worse. And pretty soon you go, wow, this is not very good. We need not to have this headache. And therefore, people have developed programs like Visual Mintech. Visual Mintech incorporates activities. You know, we were talking about activities and ignoring them. Well, Visual Mintech doesn't ignore activities. Visual Mintech incorporates activities, and it solves everything simultaneous. Everything should be solved simultaneous. We just do stepwise to make the math easier, so we don't have to deal with the simultaneous headache. And Visual Mintech is free. And so here, something that does activities and simultaneous, and it doesn't cost you anything, is pretty good, right? And so this is worth putting on your computer, maybe. Well, it's going to take up space, which is not free, you know, memory. But you think if it's free, it must be weak. You know, why would they give it free if it's very useful? And it turns out, well, it wasn't really free. This was funded by government agencies. Since it was funded by government agencies, sometimes the things that are funded by government agencies are used for profit, you know, like pharmaceuticals or whatever. You know, those were funded by government agencies, but there's a profit incentive to keep the business going. But this one, I don't know. I don't know why they didn't have the profit in here. Maybe their salaries were also funded. But this turns out to be a very powerful program. In fact, did I mention this? They're getting some kind of unusual precipitate on this space station. They use Visual Mintech to try to figure out what that precipitate is. You know. And so this is why this is part one. Part one, we're just going to look at acids. Part two, we're going to look at chapter 18 stuff. So I need to break it up since I'm not on schedule. And so we're going to look at Visual Mintech. And I thought, okay, the lab that we're going to do is we're going to do this. You know, in a titration curve, what we get is the pH versus the milliliters of sodium hydroxide. This is a titration curve. What we're going to do is we're going to use Visual Mintech not to get the titration curve. We're going to use it to get the species. Normally when we want to get the species, you know, what are all the species present, we have to do the ice, right? And we go through the ice and we figure out, you know, what are the equilibrium concentrations of all the species present. That's what we do. So if I'm here, you know, what are the concentrations of all the species present? If I'm here, you know, what are the concentrations here? And so what I want to know is, you know, what are the concentrations of all species in solution? So I can't do all the shortcuts here. You know, I did all the shortcuts because all we cared about was pH, and that was it. But now if I want the concentration of the species, now I have to go through and grind through every single step to get it, right? You know, what... so what we're going to do is we're going to generate a speciation curve. See if I can see some here. So you can see what I'm trying to do. And these are speciation curves here. So we could try to titrate things like carbonic acid, CO2, and water, you know, by adding acid or base. So we start off at a low pH, and then we start adding base. As we start adding base, what's going to happen? The pH is going to rise, as we expect on a titration curve. Of course, the pH rises, and we can monitor that, but in this case, we're not going to monitor the pH versus the milliliters of titrant. In this case, we're going to take a look at the pH and then the species that are present. So, for example, here, when I start titrating this, between pH 0 and 5, it's all CO2 and water, or carbonic acid. CO2 and water is carbonic acid. But once I get to pH 6, 7, when I get to pH 7, is there any more carbonic acid left? No, it turns out there's no carbonic acid left. They should do this different colors. Should do this. Let me do this. I'll take this off the internet here. I don't have the reference. Well, I'll grab it later. So the way we read this is like this. We start off with 100% carbonic acid all the way to about pH 5. And then above pH 5, we start to lose some of that. And so the carbonic acid is going to decrease until it hits 0. And then go down to 0 here. As the carbonic acid decreases down to 0, what increases in population? What increases in population is bicarbonate. And the bicarbonate is going to be the dominant species between, let's say, 6 and 10 or so. But as the pH continues to rise, the bicarbonate will start to decrease once again. And bicarbonate is going to go down to 0. And what's going to take bicarbonate's place? Carbonate. And so carbonate will start to rise here. And at high pHs, we expect only carbonate. At low pHs, we expect carbonic acid. And at intermediate pHs, we expect bicarbonate. This is a speciation curve. Or I don't know what they called it, partition. We called this a partition curve. Here. For phosphoric acid, it's more complicated because, we have 1, 2, 3 equivalence points for phosphoric acid. We never saw the third equivalence point, because the third equivalence point comes at pHs higher than 12. Do you see that? So the first equivalence point is here, second equivalence point is here, third equivalence point is here. So at the first equivalence point, we've neutralized, actually it's here, first equivalence point is here, we've neutralized all the acid, made base. Second equivalence point's here. Third equivalence point's out here, pH is too high. ResearchGate, this is from. This is, if you're, amino acids are kind of like this as well, because amino acids, they have a weak base, the mean part, and they have a weak acid, the acid part. And so when we look at amino acids, they have interesting speciation curves. Let's see, do we have one? Glycine, yeah, that would be good. something else. And so this is, this is they have the isoelectric point where you have a positive and a negative charge. But anyway, amino acid, you have the acid form here. At what pHs though? At what pH does the acid form occur at? And so this is why we generate these curves. You can see at what pHs this acid form will exist. And then we have this one, the zwitterionic form, in which the base is positively charged, the acid part has been deprotonated, is negatively charged now. And so this is converted. This is the conjugate acid of the base. This is the conjugate base of the acid. It's kind of funny. And then we have the base form. And so we have the acid form, the base form, and this zwitterionic form. And the pH we can determine. You can determine it using this equation here, which I think we talked about this equation earlier. This is, remember we talked about amphoteric species? So this kind of looks like amphoteric. All right, so how do we use this? What we'll do is we'll take a, say, 30, 10. Is that clock right?
11.
All right, 11. I guess I went too long. 10:30, 10:45, 11:15. Let me talk about visual MinTech first. That's not. So what we want to do is we want to learn how to use Visual MinTech here. And it's a pretty powerful program because they update this. Actually, I thought they updated this annually. This is 2013. Maybe the paid programs are taking over. Okay, so what we're going to do here, although we're just using it for acids right now, but we're going to get a little bit familiar with Visual MinTech here by looking at the tutorial. The user guide, which is still not complete. It contains step-by-step instructions for how to use Visual MinTech and what the different menus and files are for. And so let's get the, I don't know if the user guide is there, but on the computer I should check that, but let's go ahead and get that here. Well, we'll check on the computer in there. It should have the user guide on there, but we'll see. Some of the stuff for the user guide we're not going to use. And so we're going to be skipping the metals, but we'll get the acid in there. And there's a funny way of inputting the compounds that we're looking at. And so we're going to stop pretty soon and then start up over there. We're going to generate some graphs. Were there any questions? All right.